that case we start with kinematics. We derived the three formula V equal to U plus AT, S equal to UT plus half AT square and V square is equal to U square plus 2AS. Did we derive them in calculus?
Yes, sir.
Fine. Now, right now we will be dealing with motion in one dimension. For us, technically we write these equations as vector equations. V is equal to U plus AT. Now S equal to UT plus half AT square. They are all vector quantities. Implies U is the initial velocity, V is the final velocity, S is the displacement. Here S is the displacement. Now V square is equal to U square plus 2AS. Can I call this also a vector equation? The final product may not be a vector equation, but it is also written in vector notation. What do you mean by that? It is V dot V is equal to U dot U plus 2 times A dot S. Now the dot product of these two will become a scalar. Hence I will call V square equal to U square plus 2AS as a scalar equation.
Yes, sir. Yes, sir.
Have a look. Now V dot V equal to U dot U plus 2 times A dot S.
Yes.
Now what is this V dot V? It is the dot product of these two. How do you actually simplify the dot product? Magnitude of V into magnitude of V into cos 0. Magnitude of U into magnitude of U into cos 0. Right, so magnitude of V into V into cos 0 means cos 0 is 1, so it becomes V square. Similarly, it becomes U square. A dot as you write it as A into S, because you know that it is motion in one dimension. If it is not motion in dimension, I will have to keep that as A dot S. Right, if it is not motion in one dimension, I will have to keep the dot product here. I will know the direction of acceleration and displacement. Hence, this final equation is a scalar equation, but for that the vector representation is this. You can never ever multiply two vectors numerically. They should either be a dot product or a cross product. Here this is a dot product. Is the logic clear? Now what are you emphasizing on? I am emphasizing on the fact that S is the displacement. For instance, consider a problem. Initial velocity of the body is 3 meters per second. Initial velocity of the body is 3 meters per second. Fine. Have a look at this. Initial velocity is 2 meters per second and the acceleration is, initial velocity is 3 meters per second. Acceleration is 2 meters per second square. Acceleration is 2 meters per second square minus 2. What does the negative sign tell me? That the body is retarding. So when I use this formula, I will have to put a negative sign for the acceleration all throughout. But he asked you for the distance moved by the body in 2 seconds. Distance moved by the body in 2 seconds. Will you try the problem? Take this down and try this. Initial velocity is 3 meters per second. Acceleration is minus 2. Find the distance travelled.
2 meters. 2 meters.
U into T is 6 minus half A. Incidentally, that is wrong. That question is given for that sake. You were expected to fall into the trap, you fell. Now yes, here is the displacement. And what you calculated is the distance. How different are they? They are not different till when both are in the same direction. Till when the body is moving in the same direction. Till when the body is moving in the same direction. For you, distance and displacement are the same. If the body turns back, then this will be the distance, this will be the displacement. Now what makes you feel that the body will turn back? If the velocity becomes 0 at any particular point, it will turn back. It is more like throwing a body in the upward direction. When you throw a body in the upward direction, it goes to the highest point and it comes back. So there, when you threw a body in the upward direction, the body was decelerating. It goes up and it comes back. Now verify if In 2 seconds, you are asking me traveled in 2 seconds. In 2 seconds, will the particle yet be moving in the same direction, or will it come to rest and it will come back? That you will get from V equal to U minus 80. 0 equal to U is 3 minus 2 into T. That means in 1.5 seconds the velocity becomes 0. After 1.5 seconds it will turn back. So now when you use S equal to Ut plus half AT square, this is what you are getting. Ut minus half AT square. U is 3 into 2 minus half into 2 into 4. This is 2 meters. That means this distance is 2 meters. This distance is 2 meters. Right? If this distance is 2 meters, this is the total distance travelled. This is the total distance travelled. Now if this is the total distance travelled here, how do you get that? First to find out this distance using S equal to Ut plus half AT square or V square equal to U square plus 2AS. You know U, you know V, final velocity is 0. So I use V square is equal to U square minus 2AS. I will get the total displacement from here till here. The total distance minus this distance, will I get this distance? Now what he is asking you here is the total distance from here till here. I hope I am making sense.
Yes,
The purpose of giving you this example is to tell you whenever you use any one of the three equations, yes, what you get in that is the displacement and not the distance. Can I take distance and displacement to be the same if and only if they are in the same direction? If at any instant the particle takes a turn, distance and displacement will not be the same. No, fine. Have a look at this. At the first place, first let us deal with the graphs and then we will come back to the problems on this subtopic. Firstly, suppose you are dealing with uniform velocity. How do you represent a velocity time graph? This is velocity and time. Can I call this to be uniform velocity? It will be a straight line because the velocity will be the same. Now the velocity remains constant. Two main parameters that we need to understand. We will draw VT, AT, ST graphs for uniform velocity. Now the slope of this slope is dV by dt, which will be the acceleration. Now because it is uniform velocity, acceleration is 0 and hence the slope is 0. Is that okay with all?
Yes.
Second, if I want velocity as a ds by dt, ds is equal to v dt. Velocity is ds by dt, ds is equal to v dt. Integrate ds, integral v dt. S is equal to integral v dt. Right, S is equal to integral v dt. Now you were told while dealing with integration that if you integrate fx dx, right, you will get the area under the curve and above the x-axis. Now fx was y and on y-axis you have got the velocity. So now can I consider this to be fx, this to be dx? So this must give me the area under the curve and above the x-axis. This is the area under the curve and above the x-axis, and this will give me the displacement. Indirectly you are telling me area under the graph and above the x-axis for a VT graph, you will be getting the displacement. Is that okay with all?
Yes, sir.
Because you have taken velocity is ds by dt, v dt is ds, you integrated on both sides, yes, integral v dt. This gives me area under the curve and above the x-axis, and this is the displacement. Hence area under the curve and above the x-axis for a velocity time graph will give me the velocity. Velocity time graph will give me the velocity. Is that making sense?
Yes, sir.
Second, so area under the curve and above the x-axis, once you know the displacement. Now come to the second graph. It is uniform velocity, so how do you draw acceleration time graph? Acceleration time graph will be in this direction. It will be along the x-axis, so that the acceleration is 0. Right? Here, for an acceleration time graph, let us deal with that in the uniform acceleration state. This is uniform velocity. Now, how do you draw the displacement time graph? This is displacement in time. This will be a straight line because slope will give me velocity equal to ds by dt. And you have told me that it is uniform velocity. For uniform velocity, the slope should remain constant and hence the graph will be this way. Slope of the curve will always give you velocity. There is another displacement time graph possible. Here at time t equal to 0, displacement is 0. That means the particle is starting from rest. If not, the particle will be starting from here. Displacement time graph. That means at t equal to 0, initial displacement will be equal to s naught. At t equal to 0, initial displacement is s naught. What are you trying to tell me? I am starting my journey from here. At time t equal to 0, I am at this particular position. While the origin is taken somewhere back. So at time t equal to 0, I have certain amount of displacement. So that displacement is being referred to as s naught. Is the logic clear to all? The three graphs that you are dealing with all throughout is Vt graph, At graph, St graph. St graph is displacement time graph, At graph is acceleration time graph, Vt graph is velocity time graph. Right? Quick. Have a look at this. Now that was the situation when the body was subjected to uniform velocity. What if it is subjected to uniform acceleration? Uniform acceleration. Now uniform acceleration in the sense, firstly, acceleration time graph, I will have something like this. It has uniform acceleration. Previous case it was uniform velocity, so the acceleration is 0. Here it has got certain uniform acceleration. Now acceleration I write as dv by dt. dv is a dt. That means v is equal to, I actually do the integration at time t equal to 0, I will get the velocity as u. Time t equal to t, I will get the velocity as v. So this will be v minus u is equal to integral a dt 0 to t. Implies integral a dt, what are you going to get? The area under the curve and above the x-axis. Why? Acceleration is taken on the y-axis, time is taken on the x-axis. This I can compare it with integral of x dx. So this must give me the area under the curve. Then what will that be equal to? The difference of the velocity. If I take the initial velocity to be 0 here, then the area under the curve I will get the velocity at time t equal to capital T. If not, I will be getting the difference in velocity. Suppose I take this area, right? If I am taking this particular area, here there will be initial velocity u, final velocity v. So now I will get v minus u. If I take origin and I take initial velocity 0, then I will be getting the final velocity when I calculate the area under the curve and above the x-axis. Second, what do you do with velocity time graph? Velocity time graph will be this. Here, slope of velocity time graph is dv by dt, which will be acceleration. And you are telling me that the body is subjected to uniform acceleration. If the body is subjected to uniform acceleration, this will be the velocity time graph. Slope of this will give me the acceleration. Area under velocity time graph will give me what? Displacement. Previous example we have seen, area under velocity time graph will give me the displacement. Just the previous example we have done. Remember that. One more way of representing this velocity time graph, it might start from here u naught. It might start from here, this is u naught. This is the initial velocity u naught. Right? Now this velocity time graph, when the slope is going this way, the velocity time graph u naught is the initial velocity. In this case for me initial velocity is 0. In this case initial velocity is not 0. Slope will again give me the acceleration. Area under the curve and above the x-axis will give me the displacement. Area under the curve and above the x-axis is the displacement. Third, what if it is a displacement time graph? Watch out for this carefully. Temporarily, for you to understand the shape of the graph, if you consider initial velocity to be 0, will you get displacement s is equal to half at square? Because acceleration is uniform, can I conclude s is directly proportional to t square?
Yes, sir.
Displacement is taken on the y-axis, t is taken on the x-axis. That means this equation is nothing but y directly proportional to x square.
Parabola. Yes,
And
sir.
this should be a parabola. So if I draw the positive side of the parabola, the graph should be like this. The negative side will be coming this way. I cannot take time negative, so I skipped the left part of it. So the time is positive and the parabola is in this direction. Let me cross verify with two parameters here. You told me slope of a displacement time graph, you will get velocity. Slope of a displacement time graph, you will get velocity. And in uniform acceleration, the velocity is increasing. Yes, if I take the slope here, it will be like this. If I take the slope here, it will be like this. Can I consider theta 2 is greater than theta 1? That means the slope is increasing. I will have to always cross verify this. The body is subjected to uniform velocity, means the slope is increasing. Right? If the slope is increasing, that means the velocity is increasing. One small subtle difference here. Initial displacement, can I take that to be non-zero? Comfortably you can take that to be non-zero. I'll consider this to be S0. That means when I'm starting my journey, I'm standing here while the origin is somewhere behind me. So initially at time t equal to 0, you are taking some amount of displacement. Right? So this will be S0. But one very small subtle difference which you will have to observe. Initial velocity, can I look at a displacement time graph and tell you if the initial velocity is 0 or not? Now when will the velocity become 0 from the displacement time graph? I can tell you that the velocity becomes 0 if the slope is 0. So it all depends on how are you drawing the graph at time t equal to 0. If I don't want the initial velocity to be 0, I will have to draw it this way. Here u is not equal to 0. At time t equal to 0, if I draw its tangent, the tangent should not be parallel to the x-axis. If it becomes parallel to the x-axis, then for me the velocity will become 0. Now in this case, I will take S0 here and I draw the graph this way. At time t equal to 0, I am getting the slope to be 0. When I draw a tangent, see the shape here and see the shape here. Here at time t equal to 0, the slope of the curve is 0. That means initial velocity is 0. Is the logic clear?
Yes,
All of you.
Yes, sir.
Wait. And then draw the same AT, VT, ST graphs for a uniform decelerating body. AT, VT, ST graphs for uniform decelerating body. If it is uniform deceleration, have a look at it. Uniform deceleration for an acceleration time graph. The uniform deceleration will be A0. For an acceleration time graph, the uniform deceleration will be A0. Right? And it will be on the negative side. If this is the origin, I am showing on the negative y-axis. Why? Because it is deceleration, it will be negative. Then come to velocity time graph. Velocity time graph, I am starting with an initial velocity of u. And the slope should be negative because slope of this will give me the acceleration. Here slope must be negative. Why should it be negative? Because you are dealing with uniform deceleration and not acceleration. And after some time, if the body is decelerating, the velocity will become 0. It will come to rest. As a result of which it should be a straight line. And what is this? What does this straight line signify? That the deceleration is uniform. Because the slope is constant. No doubt.